We've been talking about the binomial distribution, and now I'd like to illustrate the formulas that I went over with you by doing some problems. So if you turn to about page 120 in the course packet, there's some binomial distribution problems. This, by the way, is right out of Siegel, so you'd also find this problem in Siegel. So problem 1 reads that suppose that 8% of the loans that you authorize as the vice president of some bank will never be repaid. Assume further that you authorized 284 loans last year and that they go sour independently of one another. Now, one of the first things you have to do when you read a problem like this is to start thinking about what is the distribution. Now, there's a couple things that point us in the direction of the binomial. So first off, we have a dichotomous situation. So loans are either repaid or they're not repaid. So there's a dichotomous situation. Secondly, we do this many times. So we authorize 284 loans, and we note how many loans go bad. So we're counting the number of yeses. So yes, in this case, would be a loan going bad. And we're going to see how many go bad out of 284. The third piece, which is a little bit more technical, is that the loans are independent of one another, and we need that for the binomial distribution to work. Now let's just look at, let's start by writing down what we know. So that's always a good thing. Let's go over to the sketch pad for a second, and we're going to say, let pi be the probability that a loan, so just one loan, goes bad. And n, in this case, is 284 loans. So we authorize 284 loans. Let's go back to the problem. The first part reads, how many of these loans authorized by you do you expect will never be repaid? Now, I've helped you a little bit in the statement of this problem with the italics. So these words, expect as well as how many, are keywords. Now, how many is telling you that it's a count, right? So we want to know, how many. We're going to count the number of loans, which is telling us that it's a binomial question, given everything that we've already said. And the expect part is telling us that it's after the mean. So we're asked to find the mean of the count. Now if we go back to this slide, here is the mean number of yeses. So how many yeses? Here is the formula, it's just n times pi. So let's go work problem A. We're after the mean. Well, first off, xb is the number of bad loans out of 284. So this problem is asking us what is the expected value of xb, and from that slide in the course packet, the answer is just n pi. So n times pi. And so in this problem, n is 284 and pi is 0.08. And if you do the math, you get 22.72 if you want. For the sake of argument here, for the sake of this discussion, I'm going to say that this is approximately 23. Ordinarily, I don't like to round that much, but I want to interpret this in a minute. Anyway, let's go back to the course packet and check out the next part. Part B says, find the usual measure in the level of uncertainty. Now, this is somewhat cryptic, but whenever Siegel says usual level of the measure of uncertainty, what he means is standard deviations. So we have to find the standard deviation in this problem in the number of loans. So there we go again. Number of loans is another keyword that you want to look for. What that number of loans tells you is that you're finding the standard deviation of xb. So xb comes from number of loans, standard deviation comes from level of uncertainty. Interpret this number. All right, well, we go back to this cheat sheet of shortcut formulas. We're looking for the standard deviation of xb. Here's the formula for the variance of xb. It's n times pi times 1 minus pi. So let's go write that down. So part B, we want sigma xb, which is equal to the square root of n times pi times 1 minus pi. That formula back in the course packet was for the variance. We're going to take the square root so that we get the standard deviation. Now, let's go put the numbers in. So 284 times 0.08, and then 1 minus 0.08 is 0.92. I won't write the subtraction there, but 0.92 is 1 minus 0.08. And if you do the math, this works out to be about, well, 4.57 something or other. And for the sake right now of the discussion, let's just call that 4.6. Now, the last part of this is to interpret it. So what does this tell us? Well, recall that I said that binomials are approximately normal as long as the sample size is large enough. So let's go just draw what this distribution looks like. So this is XB, the number of bad loans, after issuing 284 of them. And the mean is going to be right here at about 23. Now we have to recall something that we know about normal distributions, namely that 68% of the distribution will fall within one standard deviation of the mean. So if we go 1 sigma out in either direction, that's going to take us to, well, let's see, 23 plus 4.6 takes us to 27.6. And if we go the other direction, 1 standard deviation, you get 18.4. So if you think about this as a compound random experiment where you issued 284 random loans, 68% of the time you know that the number of loans that go bad will be between 18.4 and 27.6. I think that's a pretty powerful statement. Now, if you remember the other part of the empirical rule, and you go 2 standard deviations out, so 2 standard deviations out takes you to 13.8 on one end and 32.2 on the other. What we can say is 95% of the time you will have between 13.8 and 32.2, that should be a 2 out here, bad loans. So this kind of gives us a reasonable upper bound on the number of bad loans we might expect, 32.2. All right, so that's a very powerful thing that we can say. Let's go back to the course packet and read the last part. The last part says find the usual level of the measure of the level of uncertainty. Translate that into English, that means they're looking for the standard deviation in the percentage of loans. Now the percentage of loans is very important because that's telling us we're talking about a P rather than an XB. So I'm going to go over here and let's write part C. P is going to be XB over N, as it always is, which is the percent of bad loans. Now, what we're after is sigma sub P. How are we going to find that? Well, go back to your sheet with the formulas on it. So you see P again is XB over N. The standard deviation is going to be the square root of pi times 1 minus pi over N. So this is equal to the square root of pi times 1 minus pi all over N. So let's just fill in the numbers here. 0.08 times 0.92 divide by 284. And this is about 1.6%. It says interpret it. The interpretation is going to be about the same. The mean percentage is going to be 8%. So if this is the distribution of the percentage of bad loans, on the average you're going to get 8%. Well, you're not going to get that every time. Sometimes you get more, sometimes you get fewer. How much more and how much fewer? Well, 68% of the time you're going to be between 9.6% and 6.4%. If I did the math right there. So 68% of the time you're going to be in here. You can make the same argument with 95% by going 2 standard deviations out. So 2 standard deviations is 3.2%. So that's this problem, and I hope you can see how useful these shortcut formulas are.